I mean, actually, maybe. Oh, Andre is here.
Yeah, you could push on the live stream.
It's your day.
The live stream's up too, so.
The live stream is
I
good.
guess that probably means people are just not catching it, but it's there. I don't want a cold.
Should we go? Okay. Good morning, everyone. Welcome to Alicia's thesis defense. For those that don't know me, my name is Tim Bertram. I have the honor of introducing Alicia this morning because Tracy's a little bit under the weather. So forgive me if I forget a few details, but I think I know them all. Alicia earned her undergraduate degree from Bowdoin College. Beloit?
Beloit.
Okay, I didn't know that.
Okay.
Oh, I'm off to a rocky start here. Before getting her master's degree at UC Irvine. I got that one.
Yes.
And joining us here at UW-Madison. You're going to hear a lot about the science that Alicia has done, and I've been privy to many of those conversations, and it's such an exciting world of the interface between chemistry and regional modeling to assess the impact of the chemistry that happens at night on urban air quality. But I think we don't be remiss not to highlight some of the things that Alicia has done outside of research, which has been highlighted by things like the AOS Department Service Award. She's been a mentor for the the Science Olympiads here, and also has developed all of these super cool Python tools and tutorials that can be used to access air quality data sets and really be able to connect people that may not have the ability to access that information to be able to look at science themselves, which I think is an awesome contribution to science equal to all of the things that have been done here. So we'll have the opportunity to learn from you today, and I look forward to hearing more about nocturnal NOx chemistry. Yeah.
Okay. Can everyone hear me? Okay, cool. So thank you all for being here. I know it's very early on a Monday, but today I'll be presenting some of the highlights from my dissertation entitled Modeling and Assessing the Impact of Nocturnal NOx Chemistry on Air Quality. Before I dive into any science, I do need to thank some people, some funding agencies, and some data sources. So first and foremost, thank you to my advisor, Tracy Holloway, and to my committee members, Tim Bertram, Ankur Desai, Liz Maroon, and Brad Pierce. I also need to say thank you to the NSF Graduate Research Fellowship Program, which funded my first 2 years here at the AOS department. And then thank you to the EPA Science to Achieve Results Program grant that's been funding my research for the past 2.5 years. And then finally, thank you to Kristen Foley, Todd Plessel, and the EPA Equates team for providing a lot of the data that I used in inputs to the model. So I'll be talking about that in a little bit. But we sort of got a little bit of like a early preview to this data. So thank you to them for all of their help and support. Okay, so first and foremost, let's talk about this picture that I'm using in the background with a lovely orangey brown haze, really adding to that ambiance. So there's one category of air pollutants that create that orangey brown color, and that is NOx, or nitrogen oxides. Nitrogen oxides is the sort of umbrella term we use to talk about NO and NO2, which are two different gases. NO is emitted as a primary pollutant from things like vehicle emissions and also from things like soil. And once it's emitted into the air, it very quickly reacts to form NO2, and NO2 is the actual gas that sort of lingers around and gives us this really lovely brown color to the sky. When I was living in Southern California, so as Tim mentioned, I was in Southern California for my master's, and every single scenic photo that I took while living out there has a really nice band of like orangey brown smudge in the distance. So places with a lot of vehicle emissions like Southern California, you do get that nice NOx layer. But it's not just adding some color to photos. NOx has a number of negative consequences associated with it. So first, NOx have a lot of negative human health implications, so they can cause cardiovascular and respiratory problems. They also can lead to environmental damage. They're one of the leading components of acid rain, and actually a lot of early EPA regulations around NOx were sort of dealing with acid rain and trying to target that. They're also a key ingredient in the formation of ozone, another health air quality pollutant with health problems associated with it. And finally, NOx contribute to particle composition. In case anyone needs a reminder, this is a photo that Ruja took actually of the really lovely air quality that we had back last summer. And biomass burning events aside, NOx actually contribute to particle composition. So in these pie charts of particle composition, the red section is nitrates. Nitrates are derived from NOx. And so in sort of the upper Midwest where we are, nitrates and NOx contribute a pretty big fraction to particle composition. So for all these reasons, NOx are regulated by the EPA. And one of the tools in the EPA's regulatory toolkit to understand NOx are chemical transport models. So throughout my dissertation, I will be using a chemical transport model to better understand NOx.
Tracy said they're having a hard time hearing on the Zoom. Can we move it closer, maybe?
I did a little bit.
Is it still?
I guess I can ask. She did say, could you move it closer? Maybe let's bring it over here.
Yeah, or
Yeah, she said more.
even the laptop over even.
Tracy, is that better? Okay, I see a head nod. Excellent.
Okay.
So chemical transport models, I'll be using a model to study NOx, start my dissertation. The EPA's specific chemical transport model that they developed is the Community Multiscale Air Quality Model, or the CMAQ model. And I know there are some modelers in this room, but I want to take a moment to talk about how the CMAQ model is a little bit different from numerical weather prediction models or from global climate models. So first and foremost, CMAQ requires inputs of meteorology for each grid cell and time step of interest. It doesn't calculate any of meteorology in line. And it also requires inputs of things like emissions from vehicles or smokestacks or from plants. And so all of those emission inputs are then put into CMAQ and run in every single grid cell and every single time step to understand changes in the concentration of gas phase and particle phase species. So throughout my dissertation, the CMAQ setup that I used was a 12 by 12 kilometer grid with 35 vertical layers and 1 hour time steps. This is a little bit more fine resolution than what you might see in like a global climate model, and in each of those time steps and grid cells, your CMAQ is tracking the change in concentration of C of every species over time. And there are a number of processes that it's tracking to see how concentration changes. So there's advection, diffusion, cloud processing, deposition, aerosol processes, gas phase reactions, and emissions. The three sort of processes that I will be focusing on throughout my dissertation are these aerosol processes, gas phase reactions, and emissions. And the reason I'm focusing on multiple things is because NOx chemistry is actually pretty complex and deals with each of these things in unique ways. So the reason NOx has some complex chemistry is because different things happen during the day compared to the night. So during the day, you have emissions of NO. NO will pretty quickly react to form NO2, so in this cycle here. And then once you have NO2 during the day, sunlight can break down NO2 and contribute to the formation of ozone. So this NO2 reacts with sunlight, and you get a single oxygen that will then react to form ozone, and you reform NO, and you have a cycle that just goes around producing more ozone. But during the night, when you don't have sunlight, that cyclic reaction doesn't happen anymore. And instead, you have NO2 reacting with residual ozone, actually, to form other species such as NO3. And NO3 can then react with NO2 to form N2O5. N2O5 can go into the particle phase, so it can interact and react with particles, and enter into the particle phase where it can undergo some further reactions and either form nitric acid or ClNO2. And the reason that I'm highlighting these three nighttime species, NO3, N2O5, and ClNO2, is because they are what are called reservoir species of NOx. And this means that when you put a monitor in a location at night and measure NO2 concentration, you won't register anything from these species, but as soon as the sun comes up, they'll immediately break down, or very quickly break down, and form NO2, and so they contribute to an increase in early morning NO2 concentration. So that's what is meant by reservoir species. They don't contribute to immediate concentration, but they contribute to an increase in concentration when the conditions are right, meaning when the sun is out. And an important component to these reservoir species and their chemistry is interactions with particles. In the CMAQ model, I'm interested in understanding heterogeneous or gas-particle interactions, specifically the reactions of gas phase N2O5 going into the particle phase, my salami-looking particle, and that process of N2O5 going into the particle phase is called uptake of N2O5 or gamma N2O5, and it represents a loss of NOx because there is less N2O5, meaning less reservoir of NOx, less NOx. The second heterogeneous reaction that I'm interested in is the production of ClNO2 from the particle. So after N2O5 goes into the particle, reactions happen, and ClNO2 as a gas can come out. This is the production of ClNO2, so it represents a production process of NOx. And it's represented by this yield of ClNO2. So within CMAQ, you might guess that the particle composition and the way that CMAQ describes the particles is important for both of these reactions, and that is true. So CMAQ has sort of two ways of describing particles. The first is in terms of size. So CMAQ describes three particle sizes. You have Aiken mode, accumulation mode, and coarse mode. Aiken and accumulation mode are considered fine mode particles, and most cases, this is the mode that's assumed to have more chemistry happening. That may not really be true, but it's sort of the assumption oftentimes. And the coarse mode is larger particles. You might think of these as things like dust. The second way that CMAQ describes particles is in terms of composition. So here's my salami slice again. And in this, the CMAQ model sort of assumes a simple particle composition, that the particles are all spherical and all components of the particle are equally mixed around. A better representation might be one of those like spiral lollipops with like bands cycling in. So any location in the particle is the same as any other location within the particle or on the surface of the particle. But this is a huge simplification, and in reality, particles are not simple. They're actually pretty complex. So these are fluorescence microscopy images of particles. And each color in these images is a different component or material that makes up the particle. So the sort of green or yellowy greenish components are fresh organic material. You can think of this as kind of like oil a little bit. It's, as you can see, tends to form like a coating around the outside of this circle in black in the middle. Then there's sort of these more orangey reddish components, and this is aged organic material. So this is kind of the difference between like the fresh organic material is like olive oil that you pour into a pan, and the aged material is kind of like that nasty layer of like oily film on the back of your oven that you haven't cleaned in a really long time, and it's starting to like turn tacky and like get dusty, and there's other stuff in there. So that's sort of the difference in terms of composition. It's started as the same, but it's aged, and now it's a little bit different. And then the final component is the black interior, which is inorganic material. You can think of this as like salts and water. And so what we can see is that a lot of the organic material likes to form these coatings around the outside of an aqueous or inorganic core. The current representation in CMAQ is that this chemistry doesn't exist, and so this leads to the first guiding question in my dissertation. So we're going to go through all these, but the first question, how is the uptake of N2O5 affected by adding organic coatings to particles in CMAQ? So just sort of as a representation, visual representation, this is sort of what I added to the model, where I said, okay, N2O5 is a gas, and it goes into the particle, but first it needs to react with this organic coating around the outside, and now there's a couple of steps involved, because N2O5 could just bounce off of the particle, or it could go and interact in the organic coating, and never make it to the aqueous core, or it could eventually make it to the aqueous core. And that's actually where the chemistry that, for example, forms nitric acid or ClNO2 happens. So we want N2O5 to eventually get into this core. From a mathematical perspective, this is the code or equation that I added into the CMAQ source code. So there's sort of three parts to this that are really important for understanding the chemistry occurring between N2O5 and the particles. The first is this, what I've highlighted in yellow, and this is really asking how likely is it that N2O5 will stay in the organic phase or return back to the gas phase after it's hit the particle. The second part in green is asking how likely is it that N2O5 will react in the organic phase or diffuse the aqueous core. And the final component in purple is asking how much does N2O5 interact in the aqueous core of the particle. And really, that's where we want to get. Yes?
Alicia, are those first two really physically probabilities, or are they just represented as probabilities in a model?
So they're not physically probabilities. I've phrased them as probabilities,
Okay.
but each of these terms, so the H-org is the Henry's law constant, and it's asking basically, is something going to be in the liquid or organic phase or go back into the gas phase? And diffusion is how something moves through a fluid. So they're physical metrics. I've phrased them as
Okay.
probabilities
Okay.
here,
Thanks.
just in my questioning. Yeah, good question though. So added this source code to the model, ran the model, and then compared this parameterization of uptake to existing model parameterizations and to field measurements. So this is data from the NSF NCAR Winter 2015 field campaign that occurred over the east coast of the United States. Okay, so here are some results. So these are binned scatter plots of N2O5 concentration, where the x-axis is the measured N2O5 concentration from the field campaigns, and the y-axis is the modeled N2O5 concentration for each parameterization. And I should note that the scales are log scale, so it's a pretty wide distribution of values. The bin on the right in brown is the default chemistry in CMAQ, the sort of simplest version. The bin in the middle is an uncoated particle, but it has a little bit more complex chemistry, and that complex aqueous core chemistry in this version is actually the same as in the coated case, but now we've added an organic coating around the outside. So this is the plot that we're interested in looking in, and we can compare it sort of stepwise to the other two and say it gets a little bit less complex as you move down the line here. And really what I want to highlight is that the coated chemistry improves agreement with measurements. It's these bin medians and bin means, is red lines and brown or black squares, get closer to the one-to-one line when you have coated chemistry. And we can look at some of the performance metrics. I've just listed root mean square error here, and the coated case improves our performance with the measurements compared to the other two parameterization cases. So organic coatings, they increase N2O5 concentration, and this happens because they decrease the amount of N2O5 that goes into the particle phase. So to answer that first guiding question, organic coatings reduce uptake, they prevent N2O5 going into the organic phase, and that increases N2O5 concentration relative to the other CMAQ parameterizations and improves agreement with measurements. The second guiding question that I want to talk about, so how does changing particle chemistry in CMAQ affect ClNO2 yield? So remember, ClNO2 yield is the second heterogeneous reaction that we're interested in. CMAQ, again, has simple particle chemistry affecting ClNO2. So what happens in the aqueous core, so this is once the N2O5 has made it into the aqueous core of the particle, you have N2O5, it'll dissociate into two ions, and then this NO2 plus ion can react in either two ways in the simple default CMAQ chemistry. It'll either form nitric acid or it'll form ClNO2. But the aqueous core particles are not this simple. There are other components in the particles. So just to see what would happen when we added competitive effects and other reactions, I added this competitive effect of sulfate, and it forms various products. to this reaction. So now NO2 plus, the nitronium ion, can react with a third component to particles. So mathematically, this looks, this is the equation, so this is sort of the base default case where it's just the reaction of water and chloride, but now I've added this component here that says how much does sulfate compete with the chloride ion for the nitronium ion, and will that affect ClNO2 yield? Once again, I compared against other parameterizations in the model, and also with field measurements made during the winter 2015 field campaign, same campaign that I talked about earlier. So here is bin scatter plots again, this time of ClNO2 concentration. So measured concentration on the x-axis and modeled concentration on the y-axis. This time, the updated case, the sulfate case, is on the right, and when you have default or no sulfate on the left. And this time around, adding that competitive sulfate effect decreased ClNO2 concentration relative to the model default case. So now our bin medians and bin means are even lower than what they were before, below that one-to-one line. And you can see this in the increase in root mean square error. So it got a little bit worse. And this does make sense. Sulfate is a competitive effect, so it will decrease the amount of yield that you get. But I was a bit surprised that it really was like such a disagreement. And so when I went and looked into the model a little bit further, I found that maybe part of the problem is particle chloride concentration. So this is a frequency histogram of particle chloride concentration for the fine mode, the coarse mode, and the flight data from the winter 2015 campaign. So coarse mode data is in blue, and you can see there's a lot of particle chloride. It gets out there pretty far. In comparison, the fine mode, the CMAQ fine mode, has not a lot of particle chloride, and over 80% of the cases in the model have particle chloride less than 0.02 micrograms per meter cubed, which is just not a lot. The flight data is sort of in between these two, so the flight data is these clear hatched bars, and it has lower particle chloride than the coarse mode, but it has more than what's in the fine mode. So there might be a little bit of missing particle chloride. Keep this graph in mind because I'll be coming back to it later on in my talk. But to sort of summarize this section, sulfate competition reduces ClNO2 yield and therefore ClNO2 concentration, and particle chloride might be biasing the results of this. All right, so now we've added two new parameterizations to the model. And so the third question is, what is the impact of this updated chemistry on NOx? I started my talk interested in NOx, and so we're coming back to NOx. What's the impact of the two updated parameterizations on NOx concentration? And here's your answer. So these two parameterizations, this is a percent difference in NO2 concentration between the default chemistry and the updated chemistry that I implemented. So it's normalized to the updated chemistry, meaning that the blue negative percent difference means that the updated chemistry has higher NO2 concentrations and the default chemistry has lower NO2 concentrations. And you can see that the percent difference is higher in January than July, meaning that you have a bigger difference between two NO2 concentrations in January than in July. In fact, in July, the percent difference is pretty close to zero almost everywhere. In January, however, there is sort of an interesting spatial distribution to this percent difference. And one thing that you might note is that urban areas have pretty low percent difference. So pick a city. You have Phoenix is pretty low, Salt Lake City, Atlanta, Chicago, all of these urban areas with a lot of NO2 emissions have very low percent difference because the change in chemistry is a small fraction of the total ambient NO2 concentration. The biggest percent differences are in more rural areas. However, it's not uniform across all rural areas. As an example, I grew up in Maine, and it is a pretty rural location to be, but there's not a huge percent difference, and actually the biggest percent differences are in places like Arkansas and around the Rocky Mountains in West Texas. So what's happening on a chemical level to be influencing this spatial distribution of NO2 concentration, percent difference in NO2 concentration? So let's jump back to this reactions diagram that I showed earlier. And so as a reminder, there are two nocturnal reservoir species that can, or three nocturnal reservoir species that are of interest here. So I've talked about two of them, N2O5 and ClNO2, where N2O5 uptake is a loss process of NOx, and ClNO2 yield is a production process of NOx. The third reservoir species, NO3, can also undergo loss reactions, decreasing the NOx reservoir species concentration. So what I want to know is what is the spatial and seasonal distribution of each of these pathways, these nocturnal reaction pathways, and what's their impact on daytime NO2 concentration. So we can pull this information out of the CMAQ model and map the distribution of loss of NO3 in green here on the left and N2O5 in blue on the right for January on the top and July on the bottom, and compare them spatially and seasonally. So the first thing that you might notice is that there's more green. Actually, you might not notice it super well with this projector, but hopefully it's better on the TV. There's a bit more darker green, so more NO3 loss in July compared to January. So NO3 loss tends to happen with volatile organic compounds, or VOCs, and most often proceeds through reactions with biogenic VOCs. And that it helps explain the seasonal difference in NO3 loss because biogenics tend to be emitted more in July compared to January. So you expect more loss of NO3 through biogenic reactions in July. The one area that I just want to point out is interesting to me is this little pocket over West Texas and eastern New Mexico that roughly aligns with the Permian oil basin, where there's a lot of drilling for oil going on. And so it's possible, I haven't looked into this, but I think it's interesting that potentially it's a little bit of anthropogenic influence as well. In comparison, N2O5 loss is greater in January compared to July. And in fact, the only location over the United States where loss is greater in July than in January is over the southern tip of Lake Michigan right there. And that is because there's some interesting meteorology that happens, but I won't get into that in this talk. So for the most part, N2O5 loss is higher over sort of the Rust Belt area, Mid-Atlantic region. And to really drill into the chemistry that's happening, I want to highlight two specific locations to sort of examine the loss pathways a little bit in more detail. So I'm going to look at Salt Lake City and Atlanta, and the reason I want to focus on these is because they are vastly different areas with different climatology and meteorology affecting them. So here we have bar charts of each reaction pathway for Salt Lake City on the left and Atlanta on the right for January on top row, July on the bottom row. And so there's a couple things I want to point out about these bar charts before we get into them. So this is relative to NOx loss, meaning that if you have a negative bar, you are decreasing NOx loss, or you might think of this as producing NOx. If you have a positive bar, then you are increasing NOx loss, removing this species. So it's kind of weird because positive means you're losing stuff. The second thing that I want to point out here is the contribution of each pathway to NOx loss. So we need to count, basically this is counting nitrogens. So for the total NOx loss is the sum of for every one NO3 you lose one NOx. For every one ClNO2 you produce one NOx reservoir species. But for every two N2O5 you lose, for every one N2O5 you lose, you're losing two NOx, and that's because there's two nitrogens, or two oxidized nitrogens in N2O5. So you end up, that ends up balancing out to two, potentially losing two NOx species. And then finally, so these bars are colored so that the updated chemistry is sort of a darker color, and the default chemistry is that lighter, more pastel color for each one. So in both Salt Lake City and Atlanta, loss of NO3 is higher in the summer than the winter. This makes sense and is consistent with sort of the distribution of biogenic emissions being higher in the summer than in the winter. In both locations, loss of N2O5 is higher in the winter than in the summer. And as I said, this is true across the entire United States except over Lake Michigan. ClNO2 production is small compared to loss, and in the summer in both of these locations it's actually approximately 0. So this really highlights how ClNO2 production is not changing the total NOx loss all that much. It really depends on your loss pathways, not too much on your production pathways. And then finally, default particles, so the sort of lighter color bars, have more NOx loss in the winter when N2O5 loss pathways are more important but they're roughly equal in the summer when NO3 loss pathways are more dominant. And so this makes sense with the maps that I showed of NO2% difference, because what I changed in the model was N2O5 loss pathways and ClNO2 production. And so these being more important in the winter, changing it therefore is going to have more of an impact on NO2 in the winter than in the summer. So to answer that third guiding question, updated chemistry decreases NOx loss in winter, and the effect is greater in July compared to in January compared to July. So you have more or less NOx loss in the winter, therefore more NO2 concentration. Okay. So let's pop back. I said please remember this slide. We're going to pop back to it now and sort of change gears, because after I had implemented the ClNO2 yields parameterization and came to this conclusion that particle chloride is kind of low in the model, I was sort of wondering what to do about this. But then Dr. Kim Prather from the University of San Diego came to visit last spring. And we ended up talking about, particle chloride in the CMAQ model, and she said, well, have you looked at what's happening with sea spray? So Dr. Prather is sort of an expert on sea spray emissions and sea spray chemistry. And so her idea was, what's happening with sea spray? Could this potentially have an influence on your particle chloride concentrations? So I was like, oh, interesting. I'll go check that out. So I went and looked at particle sea spray emissions in the CMAQ model. And as you remember, I had said CMAQ has particle 3 sizes in the CMAQ model for particles, 2 in the fine mode, and then 1 in the coarse mode. And I said that most of the chemistry, or the assumption is that a lot of the chemistry is happening in the fine mode, in Aiken and accumulation mode. Well, sea spray in the CMAQ model doesn't actually emit into the Aiken mode. So one of the modes that is important for chemistry and contributes to fine mode chloride, there is no sea spray emission, which means you're missing, like, I don't know how much particle chloride. So this led to the final guiding question and chapter of my dissertation, which is looking at how much does emission of sea spray particles affect the loss of N2O5 in chemistry in the model in general. So just to sort of provide a little bit of background, sea spray is emitted when wind acts on ocean water, and you can have different sizes of sea spray aerosol particles. So you can have larger particles, coarse sea spray aerosol, and you can have finer particles. And as you can sort of see in this image, there are sort of like 3 sort of cartoonish sizes where you have the bigger particles and then fine particles and sort of the medium size. So the small fine mode, Aiken mode particles are important in real measurements of sea spray aerosol, but the CMAQ model is missing them. So I wanted to test what happens when you try different sea spray formation mechanisms in the CMAQ model. And so I compared 2 cases to the default case. So I just tested a different formation mechanism, and then in that same formation mechanism, added in the formation of Aiken mode particles. So here are size distribution of sea spray emissions. For the default case, this is just what normal sea spray emission looks like in CMAQ, and you can see there's a lot of accumulation mode particles and a little bit of coarse mode particles. And then, so for the second panel, this is just I tried a different formation mechanism just to see what would happen and test the sensitivity of the model to sea spray formation. And you can see that the emission of accumulation mode particles decreased quite a lot. The coarse mode decreased a little bit, but it was already pretty low, so not as large of a difference in emission. And then the new method with the addition of Aiken mode emissions, and here you can see, so the accumulation mode is the same as this mechanism because it's the same mechanism, just adding Aiken mode particles, and now we have this larger peak of Aiken mode emission that isn't seen in any of the other two examples. So this is basically saying that, yes, I added in Aiken mode emissions into sea spray in the CMAQ model. But this is just emissions, and only in areas that have ocean coverage in the model. If we want to look over the entire United States and see the impact on particle composition or concentration over the entire United States, so what actually happens is this sea spray emissions, this tiny Aiken mode hump that we see here, increases the total particle number concentrations across the United States on average by 241%, which basically means that Aiken mode particles, there weren't a lot of them because you're not emitting all that much in terms of sea spray, but it's increasing the total particle number concentration by quite a lot. So there might be other sort of missing or underrepresented emissions of Aiken mode particles in the model. And then the accumulation mode, so you can see there's a decrease between the default case and the updated case. And across the entire United States, this is on average a 17% decrease in particle number concentration, which means that even though there is a big decrease in emission of Aiken mode or accumulation mode particles, it's not actually that much of the total fraction of accumulation mode particles in CMAQ. Considering how big of an impact the emission had on particle number concentration, I wanted to then see what the impact was on the loss of N2O5, which happens in both the fine and the coarse mode. So here are frequency histograms of the fraction of loss of N2O5 that occurs in the fine mode compared to the total loss of N2O5. So in the default case, most of the loss does occur in the fine mode, but it's not quite as much as what happens when you add more Aiken mode particle emissions to sea spray. So now fine mode really dominates total N2O5 loss in the model when you add Aiken mode sea spray emissions. And again, this does highlight how small the total particle concentration in the CMAQ model, or Aiken mode particle concentration in the CMAQ model was with the default case compared to the Aiken mode case. So to sort of answer that final guiding question, the emission of Aiken mode sea spray particles increases both the number of particles in this mode and the fine mode loss of N2O5. So you might be wondering, Alicia, you started this out talking about chloride, but you haven't talked about chloride in your results yet. And that is because the composition of particles changes in each mode. And so first we want to just see what change happens when you just add in this new mode. So further questions to explore, though, are what happens when you update sea spray composition, and then potentially other sources of chlorine, such as road salts. You all in Wisconsin know there's a lot of salt that gets spread on the sidewalks and some on the roads. And so what is the contribution of something like road salt to particle chloride? So these are further questions to explore. If you stay around for a little while, you might hear a master's thesis in a year or two that talks on some of this information. But I will not be talking about this or in the near future. So for me, my next steps, I'll be heading to the University of Leeds to be researching chemistry affecting the Arctic. So really winter conditions and really dark conditions. So those are my next steps. And I want to say thank you to everyone for paying attention. 9 a.m., I know it's tough. But also I want to say thank you to a bunch of people who have supported me along my journey. So thank you to everyone in the AOS and the Center for Sustainability in the Global Environment, Nelson Institute. So I sort of have 2 offices, 2 homes here on the UW campus. So thanks to everyone in both AOS and SAGE for being such a welcoming, supportive community. Special shout out to Pete, Christy, Dee, and Laurel Fletcher over in SAGE, because I don't know where I'd be without these magical, amazing people. They deserve so much praise. Also, a huge thank you to the Holloway group. You are amazing, and I will miss all of you when I leave. And then also I want to say thank you to my non-UW friends, especially my knitting group. Really great place to vent. And then finally, thanks to my family, as represented by my dog. But also there's some like human people as well that I want to thank in there. Yeah, so thank you all for listening, and I believe I'll take questions now. Kara, I think normally we do at least a student first, and then
Yeah.
so Kara.
I think I know the answer, but the comparisons that you made in CMAQ, that included both of the changes you made in the CMAQ source code, so the competition and the increase from the code.
Yeah, so if you're talking about this figure, then yes, it was the completely updated case, including both the N2O5 uptake organic coatings and the ClNO2 yield affected by competitive sulfate. Yeah, Hamish.
Nice one. How confident are you with the sources of NOx in CMAQ? And like you were showing us improvements in your chemistry from those, but could they be from the sources themselves in CMAQ, and
Yes.
could those be improved to get better results?
Yeah, absolutely. So I'm going to hop back actually to this slide. So most of the sources of NOx in CMAQ, emission sources of NOx, are inputs that you added. So you have emission inventories, for example, of vehicles on the road and how much NOx those vehicles emit, and you have model representations of soil NOx emissions, for example, and then you add those model results into the CMAQ model. There is some chemistry in the model that can affect these emissions, but for the most part, the sort of NOx sources are emission inputs that I have pretty high confidence in, but we do know that they're not perfect. You have to take, for example, a fleet of vehicles that's driving on the road, and then allocate those vehicles to a grid, a fixed grid. So there's going to be some discrepancy there from reality. Yeah. Rudra.
So building on the same question, I'm curious about do the emissions from the sources remain constant across all seasons, and then everything that's coming out is seasonality, or the emissions also change for each month?
Super great question. Yeah. So emissions do change seasonally, and some of those, most emissions will change seasonally, like if they need to change seasonally. So soil emissions, for example, biogenic emissions will change seasonally, for example. But there are some. I'm going to stop there. I don't want to get too much into it. John, did you have a question?
Yeah, on slide 40, Alicia, what's going on over the Gulf Stream?
Let's see. Slide 40 is this guy. Yeah.
Yeah. So that's striking. That's probably the biggest difference anywhere on that regional domain. So what's going on?
Yeah, so great question. Relative humidity has a big impact on N2O5 uptake. And with higher relative humidity, you expect more particle water, so you expect more N2O5 uptake, but if you're an organic coating that's blocking uptake, so you might get, in the default chemistry, more uptake over water.
Okay,
but then if we have an organic coating blocking that uptake, large decrease. That's my hypothesis. It's definitely something that I could be looking into further.
That's really good. I like that.
Yeah. Brad.
Following up on that, this one doesn't include the Akin mode and the sea salt.
Correct.
How do you think that might change?
Yeah, so that's another good question. I think that you would see more N2O5 loss. So I think it actually might balance out some of that big dark blue area over the oceans. Yeah. Tara,
I'll
okay.
ask you later.
Okay. Any other questions? Yeah, Rudra.
So I have one last question. On slide 11, you broke down the entire NOx budget stuff and focused on the 3 terms.
This guy.
Yes. So
Yeah.
can you tell me what are the relative importance or contribution of each term and how much the last 3 will count for the total NOx changes?
Okay, so that's a good question and a lot of in-depth. So, in terms of emission, gas phase, and aerosol phase, so emission is always a production source of NOx, and that's all basically our ambient levels. And actually, so I'm going to really quickly, well, actually, I won't hop back to it. So that map of percent difference, and I said that urban areas you see almost no percent difference, and that's because there's so much emission of NOx. Chemistry, the rest of this, anything I changed didn't matter. So in urban areas with a lot of emissions dominate the NOx changes in NOx chemistry or concentration. In comparing NO3 loss and N2O5 loss, N2O5 loss is mainly aerosol processes. NO3 loss can occur through aerosol processes. A lot of the literature says that that's a smaller fraction though, and most of it is lost through gas phase reactions. So in that map of percent difference, when NO3 dominates in the summer, that means gas phase reactions are mostly dominating in that case. In the winter, aerosol reactions become a little bit more important. And one thing I will say is that I didn't talk about some of the other loss processes that can happen. So deposition, for example, in some instances, in some locations, could be a really big thing. So if you have a really heavy rainout event, there's a lot of wet deposition. That's a big factor. Dry deposition is not quite as important, but it's sort of, yeah, a process that does happen. And it's, the literature and some of the preliminary research I did said that dry deposition is a little bit more important in places like Salt Lake City and other dry places with, low humidity. The other 3 processes in here that I talked about, advection, diffusion, and cloud phase processing. To clear up maybe a little bit of misconception, in CMAQ, cloud phase processes, so that's actually not like cloud condensation nuclei and forming clouds. That is reactions of gases in existing clouds. So that's more of it's affecting things like NO2 and a little bit of NO3 and a little bit of N2O5 because they can react with cloud phase water, but that is, based on the literature, not a huge fraction of total loss. Yeah, and then advection and diffusion depends on location, meteorology, and yeah. Yeah, Pete.
First of all, a bunch of congratulations online.
Thanks.
And Noah Chen has a question. She says, is the new parameterization with the Aitken mode available for other models? I imagine it would be important for cloud condensation nuclei composition for marine meteorology.
Yeah, so that's super good question. So all of the base sort of sea spray aerosol parameterizations, I didn't come up with them. They're existing parameterizations in the literature, and I found one that I thought was one of the better new representations that I used, and then added in the possibility for Aitken mode particles. So basically had to update the way that CMAQ deals with emission sources, like how the model processes different emission pathways. So it wasn't quite a chemical change, it was sort of a Fortran code change that happened. So I would assume that it's possible to implement any of those parameterizations in other models. I am not familiar with how sort of detailed like a global climate model is in terms of its sea spray emissions, so I am not sure if that level of granularity of what happens in a chemical transport model would translate into a global climate model where you really are concerned about particle emissions and how that will affect like cloud formation, for example. But yeah, it's an interesting question. Yeah, Gerald.
Did you look at how this downstream impacts ozone?
Yeah, so super great question. As I had mentioned in the beginning, NOx is a key ingredient, a precursor species to the formation of ozone. and so these changes likely would have impacts on ozone. I did not look at what the percent difference in ozone concentration is, but that would be an interesting next step. My hypothesis is that it would actually be a pretty small percent difference because the ozone season is more in the summer than the winter, and the percent difference of NOx in the summer was very, very low. That's not to say there wouldn't be any impact. There's sort of an interesting wintertime ozone that can form in especially snowy, sun-glinty places, so in Wyoming, for example, and so it's possible that you would have an impact on specific localized ozone events in the winter in places like that. Yeah, yeah, Gerald.
Just the final question, would you say based on your work you recommend that EPA adopts a coding around the particles into the standard version of the model, or do you say there's more work to be done?
So I would say that I think the more chemically representative that you can be in a model, the better. So I think the organic coatings would be a good update to include in the next version release. That said, there are probably changes to the source code that I created that would maybe address some of the issues that I saw when I was analyzing the data. So I think that there's further work that can be done to sort of fine-tune the parameterization, but I do think that the more chemically representative you can be, the better. Yeah, Kara?
Sorry. This is kind of off that. If you were to include, how did it change runtime or computational resource use?
So I did not actually specifically assess this. I didn't notice any change in the runtime. That said, I was super lucky and was able to use the SSEC supercomputers, and so, the difference of an hour over 2 days, if it added up to that much difference in time, is not a big deal, but if you don't have that sort of high performance computing power, then it might add up to a big time difference in runtime. So that's a really great question. I don't actually know. That's something probably CMAQ maintainers at EPA would probably look into. Yeah. All right. Is that it for questions? All right. Thank you all so much.